right, it's gonna be the last video for paper 2. If you're in 4th period, then you saw me like feel really dumb and kind of all of us almost trying to figure out what seemed to be extremely obvious and should have been obvious, trying to figure out what the answer was to this question about the hydrothermal vent, mainly this question AI. And okay, so I keep telling you, humans write this test, right? So the answer is not 29. If I look right here really quick. No. Okay. So it's not on there. I was able to find, it's actually through Brevard County, an example, like test worked out of paper 2, and it looked like it may have been from a Cambridge training. If you're signed up to take A level, good for you. But I'm actually doing an online Cambridge training for this class in AS and A level over the new syllabus for 3 weeks, and it starts May 4th. So everything that I have built this entire year and will just be improved, and yeah, it's very helpful. So, anyways, the answer is relatively obvious, right? Like, I'll kind of show you like what I see here. Instead of seeing like a graph, like you can actually see the shape of the actual vent. But um, yeah, the answer, the mark scheme, the published mark scheme is not correct, and yeah, the answer is a lot more obvious because then the mark scheme says 29. So then I was like, oh my gosh, like, all right, let me try and figure out how this can be 29. And so then I did, but it only ended up being 29 if I was measuring the dissolved sulfide. But I'm like, this shouldn't be. Plus, like with 4 different abiotic factors, how would somebody know on a test, like, well, you obviously you shouldn't have measured this one, it had to be dissolved sulfide. So we'll fix that right now. And if something like that happens, you wouldn't know on a test. You'd be like, oh, this seems obvious, I'm going to put my answer. Cambridge is going to get all these tests back and they're going to be like, huh, why isn't this the answer that I put? And then they realize they did something wrong. And truthfully, this has happened to me so many times as a teacher in the 10 years I've been teaching. I've realized my mistakes based on like, why are so many kids getting this wrong? Or I see answers from somebody who typically gets all of their answers correct. And I'm like, huh, why did they put that maybe? It makes me like re-question like my thoughts on it. So, okay. So with that being said, um, the mark scheme, give it grace and trust yourself because like I know like you probably feel like confused or maybe even like doubting yourself whenever you're like, this answer seems simple. Why isn't it like that on what Cambridge says? I feel that way too, right? I'm like, I'm supposed to know this, and this is not what it's published. So there was another source that I saw, and you could probably Google search it. I just searched Brevard County ACE Marine Science paper 2, or even just ACE Marine Science. And then yeah, I can't tell you exactly what the link looks like, but anyways, that's that. So I'll show you how to get this one right, and then the rest will be easy peasy. All right, we shouldn't be doubting ourselves because of somebody else's mistake, you know? All right, so we're looking at measurements of a hydrothermal vent and dissolved sulfide, dissolved silicates, and oxygen. These things are going to be coming out of like the actual vent itself, because remember how these are formed. Cold water seeps through the cracks of the ocean crust, right? Because these are formed by divergent boundaries, or like where your plates are spreading apart from each other. Um, not on the boundary. It's not happening on the boundary. It's, that's where you're going to have new seafloor coming up. And we can tell that through magnetic striping of the seafloor, just on paper 1. It could have been an answer you put. There's magnetic striping on the seafloor. We see the age of the crust being really young right here and then older over here. Um, anyways, but yeah, you got that cold water, and we like made the like step-by-step cartoons for it. Seeps through the cracks of the ocean crust, and then it gets superheated by the magma chamber. And then as water gets, there's magma chamber, as water gets really hot, it decreases in its density. And then now that water is really hot and it gets shot through those cracks in the floor again. But as it does that, it is able to like actually dissolve the crust of the earth around it. And so it's going to have a ton of different minerals in it, metals, minerals, all those. And then it comes back through, and the bottom of the ocean is really cold, and it's coming through with really high pressure. This water is superheated. It's so hot, and like so hot that it can dissolve the sides of the freaking earth. It's so hot. The bottom of the ocean has really high pressure. It's about 300 atmospheres. So that question one on paper one, where it said a decrease in atmospheric pressure, sorry, or like an increase in depth. What does that do to gas solubility? Um, the pressure actually is going to cause gas solubility to increase because even like sodas, whatever, anything that we drink that is carbonated, we like it cold so that it holds the carbonation well. And we also like it like with a nice sealed cap or like a screw top on it or something. So under pressure as well. Anyways, when that superheated water with the dissolved sediments in it reaches the actual bottom of the seafloor, the pressure is really high, the temperature is really low, near freezing. It's near freezing, like surrounding the vent, everywhere right here. But right at the vent, it is like close to boiling, which is one of the things that makes it a really extreme environment. And then those sediments will precipitate or solidify out of solution and start building up this chimney. And then inside this plume of gas, of course, you got hydrogen sulfide. Hydrogen sulfide is the like energy molecule for chemosynthesis. Huh, you didn't have a question about chemosynthesis. Maybe you'll have one tomorrow. Okay. So, and it says there's a pen, as a sensor slowly passes through the hydrothermal vent. So like you're seeing the measurements as a sensor is slowly passing through it. So if we're looking at the graph, don't be intimidated by graphs, embrace them. They have answers on them. You just need to realize how to read it. We always say like as the X is changing, so the distance that the sensor is moving, I don't like that thickness. The distance the sensor is moving, right? We're starting here. Here's its starting point. And then it's moving along. How is this, the relative, which means in comparison to each other, and of course in random units, how are these different things changing? And you have dissolved sulfide, temperature, dissolved silicates, and oxygen. If you want to just look at those one at a time, fine. But it's the same thing, whether there's 4 on there, 2, 1, you read them the same way. Okay. So for the sulfur, for temperature first, I'll do temperature. I will just highlight that one red. Something that is a good test taking strategy. Again, you cannot highlight your own graphs. You can't highlight your own answers, but you can highlight the figures that they give you. I would put some color on these because otherwise now you're going to have to decipher different thicknesses of lines, different textures of the lines. That just sets you up for a little bit more error, you know. I'm confident in reading graphs, but I know where it's going to help me more, and seeing these in color is definitely going to be more helpful. Because then I have to remember, oh wait, this one is the dot. I don't like that's. This one is a dash. This one is an open circle. Okay. What else? Oxygen, I'll do that one in blue. Oxygen is relatively high at the bottom of the ocean because you got high pressure and it's cold. Cold things hold gas as well. It's gas solubility, which is chapter 1. But you guys know like the physical and chemical oceanography pretty well. And when I say you guys, I'm talking about like my current AS level marine class, which is why I was like okay with rapidly going through ecosystems, provided, as long as you were following with me in class, managing your time, staying disciplined in the things I was making for you and giving you, like the mangrove note sheet, reading it. I did the notes for you, but as long as you read it and kind of like, okay, like highlighted things that, that, and that's just part of being disciplined. You should have done well. The harder things I try and teach with mastery first. Okay, so we have dissolved sulfide, dissolved silicates, orange. I don't want to do that because orange might be too close to that red. Silicates is like actually what sand is made of. I think diatoms have a lot of silica in it. Glass is made of silicates. All right. And then sulfur, let's give it the purple. And it's not dissolved sulfur. Sulfur is just an element. It's a sulfide, so it's an ion. Like chloride. Something to think about too, just coloring in these lines. Consider what was hit really hard on paper one. And if I have to like eat my words, I'll eat my words, fine. But those things really won't be predominantly tested on paper two. So they asked you a lot about mangroves. I wouldn't expect you to see that again. They asked you about your tectonic plates. You will do a biological drawing. You absolutely will. And I don't think it would be a fish, because the fish was already tested with labeling the operculum in the lateral line. You'll absolutely have to do a mark and recapture formula, and maybe even have to like redesign one of those, like describe how you would do this. Even though you had to talk about the limits in paper one, perhaps that might be what you to do. Okay, so if we don't look at this as, don't look at it necessarily as a graph right now, so you can kind of see what I see. I'm going to erase this, but this is the bottom of the ocean, right? It's the seafloor. They're looking at a plume from a hydrothermal vent. I'm calling this thing because it's dark, and then I'll get rid of it. There's your cracks in the seafloor. That's your hydrothermal vent. Here's all the gas coming out of it and surrounding it. There she is. Right? And so here you would have like your tube worms living on there. They do chemosynthesis. Oh, ew, gross. No, they don't. The tube worms are consumers. Tube worms would be like your coral organisms. And what's inside the tube worms is chemosynthetic bacteria, and they perform chemosynthesis. And you're like just similar to the zooxanthellae living inside the coral. It's so fun. It's just ecology, so fun. Okay, so this is essentially what you're looking at. You are looking at the actual like vent itself. This is it. This is it. And so surrounding it, right, because it is round. Surrounding it, you're going to have all these different dissolved substances. Let me just clear my lovely mess. And as always, I like to make sense of what I'm seeing. All right. Before I even read a question, but it does say suggest the diameter of the vent plume. Before I'm reading this one, I'll try to make sense of it. So we can see that, right? You have high oxygen here, and then all of a sudden, bloop, it plummets. Bloop, it plummets. What's causing it to plummet? It's either going to be silicates, temperature, or dissolved sulfide, it's temperature. So remember, we've talked about this all the time throughout the year. Temperature, high temperature is going to cause there to be low gas solubility. So that actually is this question. But again, I like to look at a graph and try and make sense of it. Dissolved silicates, dissolved sulfide, and temperature, they both increase like right around this area. And then it's high, 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 and then they decrease around the same area. And that's because that's the end of the vent plume. Like this area, this is a vent plume, this whole actual vent. All right, so if we look at the graph, we start to see a counting, right? We start to see a pretty big spike. I'll use a different color. Right here for the sulfide. Right here for your temperature. Right here for the silicates. Those things come out of the vent plume. And that's coincidentally when you see oxygen start to rapidly decrease because that temperature change, and it was so hot, the oxygen cannot stay in solution. So it rapidly falls. That's going to be where the vent plume starts. Okay, and if we're looking down here, 30, and then you got 10 boxes, and then it gets to 40, so we're moving 10, like a value of 10, and there's 10 things in between. Obviously, each box is going to equal 1. So here's 30, 31, 32. It's 32 on this. Did you say 33, Ollie? Nice job. She can count to 100. And then where does it come down? Like the edge of the plume, right? So we're looking at like this part right here. So this would be like your 32. The sensor that moved over. Where does the end of it happen? So what is my purple? The sulfur. All right, and then this one comes down and then stops and then flatlines again back to its baseline that you saw right on the other side of it. So that and then that. Same with sulfur, normal sulfur, very high at the plume. Yellow, silicates. All right, and then yellow comes down, 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 and then it's like right here, right here. So essentially it's this area. All right, and like temperature will diffuse essentially. Radiate. It's not a subject. It's not a substance. Radiate. It'll radiate through the water. And the temperature change is so great from like close to freezing, but it won't freeze because of the because when water freezes, it will rise to the top. But yeah, anything frozen will move to the surface because it's less dense. But the water boiling will boil because of the pressure. So the temperature change is so great. You can see like this must be maybe like the center, like maybe where everything's kind of coming out of the plume, maybe like part of its hottest area, and it is the hottest area. So this is where it starts to leave. And then as it gets farther, the oxygen starting to increase again as it gets further away. Likewise, when you start to see, and I'll put this now actually in blue, when you start to see oxygen increase again, which is, well, I have it color coded, otherwise this would be weird to talk about. you start to see the temperature fall pretty fast. This red line, your temperature falls at this like the same time that the oxygen is increasing. All right. So essentially we're looking at 72, and then over here where all of these guys start to increase, 32. So we're going to start at 32 and end at 32, and they want to know the diameter of it. So it like the width essentially goes from 32 to 72. So how wide is it? Centimeters. Diameter, you need a unit, and it says include the unit. 40 centimeters. 2 marks. 1 mark for the centimeters, 1 for the correct answer. I don't know why that thing's 29, and bless your heart if you tried to decipher what makes it 29, because so did I, and then I felt so stupid, and it's no good. With reference, Olive Grace. With reference, describe which means what, and explain which means why. So what do you see and why do you see it? The relationship, oof, all these just lovely, juicy words, between dissolved oxygen and seawater. All right, so what is the change, or how do they correlate with each other? The relationship between the dissolved oxygen, which is your blue line, and seawater temperature, which is our red line. Okay. I think you already know the answer. You should already know the answer because you've done this so many times. Um, I actually am trying to get used to, like, when they're saying with reference now. In the previous syllabus, when they said with reference, like, you better be referencing data and just bringing out an example. Mainly it would be like, for example, it decreased this much within, as the temperature increased this amount, the oxygen went down this amount. And you essentially always say, like, when you're trying to use an example and you're saying something's changing over time or changing with another variable, just subtract it and show the difference. Like, here's what it was, here's what it is. This is the amount of change. It doesn't seem like that's the strictness they're looking at this year. I'm still trying to, like, understand, like, that difference. I don't know. It's like when you're so disciplined to do it one way and then they change it. Why? What is life? Okay. All right. Describe. So what is the relationship? Here's that wonderful sentence. It's dissolved oxygen and seawater. So as the, think about what controls what before you start writing it. I know that they said it, dissolved oxygen and seawater, but before you even write that, consider what is controlling the other. Is oxygen causing the ocean temperature to get high or low? Gas doesn't do that. Or is the temperature controlling whether oxygen can stay dissolved or not? It's the temperature. So even though, and because I was just about to write that, and I was like, dissolved oxygen. Think about what's controlling what. So as the temperature increases, we see it spiking up really high right there, right here. The dissolved oxygen decreases. Likewise, you could say the reverse argument. When the temperature falls down again, when it's moving away from the vent plume, your oxygen goes back up. So as the temperature increases, the dissolved oxygen decreases. Okay, that's the what, and now we need to say the why. Okay, we know oxygen or gas You can say oxygen because it's specifically referencing that, but gas is less soluble. All right, and I don't need you to go further and say because the kinetic energy of the water or anything like that. Explain why. So explain is like why and how, but they already told you why. Focus on the command word. Don't care for that color. Don't care for that color. Dissolved sulfide is relatively high concentration in a hydrothermal vent plume because it's coming out of the ground with everything else, like out of that crack in the seafloor. That's why. Ugh. Okay, this question essentially is saying, why do minerals come out of a hydrothermal vent? Okay, hold on, just sulfur dissolves. Okay, and this is, you got to choose any three of these. All right, I'm just going to go for what I already taught you. So the mark scheme has it like in a different order, but it doesn't matter. So hold on a second. Okay. But I'm going to say, I'm going to reference specifically the sulfide. This year they're calling it fissures. That's fun. They are cracks, but fissures are like breaks in the ground. All right. And then previous syllabus, we need to say superheated, but gets heated. And I'll just put in parentheses for you. It's not part of the mark, but it's near the mantle. Remember, your plates actually float on the asthenosphere, which means plasticky. They move independently of each other. Just because one moves to the right doesn't mean the other one's going to move to the right. And then underneath the asthenosphere is the mantle where you have your magma. And then you got the inner core and then outer core. Nope. Outer core and then inner core. That wouldn't make sense. Okay. Not a slash. You need to include this. I will do a slash because I want you to say and. No saying and, you'll contradict yourself. Waters force up cracks. I don't want you saying waters force up cracks either. I don't like that. Because unless you're going to say as water is forced up the crack in the seafloor or the fissure in the seafloor, you can say crack, it's fine. It dissolves minerals or specifically say dissolves sulfur from the Earth's crust. not trying to say and, dissolving minerals. It's forced up with really high pressure or really high temperature. It's so hot that it like dissolves the minerals there. High pressure, high temperature. And then the sulfur exits the vent I would say forming a chimney. It's not the only thing that does that, but yeah, sulfur exits the vent. But mainly you want to say how it gets there. So it's going to be the cold water moves into the crust, gets hot, dissolves sediment, forced up. Because the temperature is so warm, like the density difference is so great because it's like psh, like shot back up like a geyser essentially. All right, cold water seeps through the cracks in the Earth's crust. The water gets superheated by the magma chamber near the mantle. Heated water is forced up the cracks, dissolving minerals or sulfur, and that's due to the pressure and the temperature. Sulfur exits the vent. I'll say like solidifying. That's not really part of the that specifically isn't really answering the question. That last thing that I wrote, why is it relatively high? Essentially, it's all of this. The sulfur dissolves, yeah, dissolving minerals, high pressure will move it back up. This mark right here essentially answered too. Explain how chimneys, oh, I just answered it. I just answered it. I say again because it came from the ocean floor. Minerals precipitate or solidify out of solution, like precipitating out of solution is becoming like a solid whenever you're mixed within a liquid or out of the water. All right, and then the minerals, we can reference salts, accumulate. Sophia, stop. Holly, tell her no. Forming a chimney. You didn't get any questions about hydrothermal vents on Wednesday, so you can definitely assume that's going to happen again, or something about chemosynthesis. Maybe if you say chemosynthesis, good for you. It happens at the underwater volcanoes at hydrothermal vents. She's 4. She's 5. She's turned 5. I would maybe like redo that, like walk yourself again, like through that cartoon assignment where like you had the 5 different steps you had to do. I only made you do those things for literally situations like this where it super matters. You guys, it's our last question. 1, 2, 3, 4, and 5. All right. Figure 6.1 shows the amount, I hate saying concentration, but yeah, the amount of nitrate ions. I'm going to stop right there. Why do we need nitrate? We need it for DNA, RNA. I don't even know if they're going to ask what is it for, but I don't care. I'm just going to say it anyways. DNA, RNA, proteins. ¿Qué más? NPK, nitrogen, phosphorus, potassium is usually with some fertilizers. So maybe like algal bloom. Amino acids. Okay. Above the abyssal plain in the North Atlantic Ocean, down to depths of 160 meters. Okay. Notice the unit, even if you're like, what is a mole or an M mole? It's a micromole. Who cares? You don't need to know it. You just need to duplicate it. And it's to the cubic meter. So like in an entire meter, right? They're saying, assuming this box is a meter is like 3 feet. They're saying like within this box, this is the amount of nitrate essentially that's like dissolved in the liquid. Okay. Don't look at this graph like it's weird. Like why isn't there a bottom axis? Consider what you're doing. You're looking at it like as depth increases. So we've done these a lot, and I was like, give yourself some waves. Let yourself see this like it's an actual like surface of the ocean. There's no need to let yourself get confused about that. Okay, so it's like very low right here. And then it starts to increase, right? Your nitrate ions are increasing as it gets deeper, all right? Describe the pattern shown. Hooray. Okay, we can say just in general, what is the depth doing? And depth is the thing that's changing. So, and what we're measuring then is the nitrate ions. The depth is what's causing the nitrate ions to increase. It's not like if you add in, it's not the other way around. This is your X in this situation. It's only flipped like this because they're showing you like a profile curve with the ocean. If they actually had it like this with like depth down here, that would just seem strange because it's the ocean, so we can actually see that like it's like a cross section. Anyway, we've done this so many times with like the thermocline, halocline, pycnocline, but it's the fact that depth is increasing that is causing like these nitrate ions to increase at different levels. It is not the fact that nitrate ions increase, it makes the ocean deeper. I tried to weed this out of you guys a lot in first semester. Like it's not oxygen making the ocean deeper. It's not temperature, it's not salinity that makes the ocean deep. It's the fact that the ocean is increasing in depth, and that's going to cause different factors like pressure, for example. Or even just things sinking. That's going to cause these factors to be different. So describe the pattern shown as pretty much like what. It doesn't say why, but like what do you see? So just in general, as our depth is 0, 20, 48, it's increase. I know that looks like it's decreasing, but depth is increasing. We're low where it's shallow. Then we get higher, and then it gets higher again, right? This is nitrates getting higher when they're moving this direction. And then it's getting higher, moving this direction, still increasing, still increasing. Higher and higher and higher. If this line went like this, right, that would mean you're moving in this direction on your axis. It's not, and that would mean it would be getting lower, but it's not. So we can say that in general, and then we can maybe give out some specifics like they want. Remember, it's depth that is causing the change in the nitrate concentration. It is not like, hey, if you want the ocean to be deeper, just add in some nitrates. It's not changing it the other way around. Depth controls it. And you're going to write concentration, not counts. Do you see anything else that's a little bit different? And within this line, like it is not like a constant change. So that's what I'm asking. Like, do you see anything that's a little bit different? Like, is there an area that maybe increases more than another? Or doesn't increase more than another? When it's increasing, it's not depth, it's nitrate ion. We're going in this direction. Right here. That's the slowest increase. Remember the thermocline? We would draw that out. And this area right here had a very little change in temperature, right? Like if this is 0 and over here is 30, Olive Grace, thank you, please put this back. Like this, from here to here, just this area, that's not a big change. That's not a big delta at all. Here, what are they counting by, 0.25? No. Is scare you? 0.05? Yes. 1, 2, oh shoot. 1, 2.5, 3, 4, 5. Yeah, it is. Okay. Hats off to me. 9. And then at 40, it's at this. So it's starting at 0.05. And then it just goes to 0.1 versus like here, just at that depth alone, 50. You got a big change. You go from
40 to 2.
Yeah, 0.75. 0.75 to 1. Same with right here. 40 to 2, Ollie. Same with right here. This is also a very little change. Going from here to here, so like just this distance. It's not that great of a change. Okay, we can add that though. It's 0 to 40 meters. So that increases by a little more than 0.25, like 0.3. Were you, let's see, right here, we're at 0.1. 0.1. And that's counting by 0.05. So 0.6, 0.7, 0.8, 0.9. Okay. Good job, babe. This is 0.7. So that's a change of 0.6. This one was a change of 0.3. In a moment, baby girl. From here to here, This one is a change of 0.5.
Yeah.
Here to here. I'm almost done, babe. Funny, funny, funny. Okay, so yeah, this is actually going to be your greatest change. From, what was that from? 40 to
100.
50.
5.
Are you sure 55, Ollie?
54.
It's actually this whole area right here. And you can kind of tell because like this is straight. This one is like slow fall, but then you got bloop, that whole area there. It's like halocliny actually, the greatest change in temperature with depth. I feel dumb I didn't see that like sooner. Yeah, it's like this one's gonna have the biggest change like moving across it. So when you are describing the pattern because you're not it's not this straight thing right here like, well, as depth increases, so does nitrate concentration. It doesn't look like that. You had this slow, come on, stop moving. Slow fall with depth, then whoop, and then another slow fall. But this part is the one that moves over the farthest. Calculate the percent increase in nitrate concentration in the region between 40 and 80 meters. Okay, so the percent increase. So here's what, when you're doing a percent, it is part over a whole. So where's your, essentially like, where did you start minus where did you end? All over your starting point. Like, here's what you had, here's how it changed, and here's what you ended with. Figure out how it changed. All right, now what portion of that was like your entire thing from the beginning? Or in other words, initial minus the final. All over your initial. But that's like, you wanted a change. Okay, there's your start to end. Now, what portion of that change? Well, what's essentially your 100% is like your starting point. This is like everything I had in totality in the beginning, and this is the difference in it. So, like, how much did it change in relation or in proportion to the start? Percent change. And it said from 40 to 80. I'm going to erase some of this so that I guess, so I can like read those numbers better. Okay, dokey. 40 right here. And I already wrote down it was 0.1, right? Yes, each box is 0.05. So what, right? No. Yes. Each box is 0.05. So why I wouldn't put one there. Hold on. This is why I needed just do better. There's 10 boxes there. 0.5 divided by 10. I'm such a poor soul. Okay. So I'm moving, my value is 0.5. I'm splitting it up 10 ways because I have 10 boxes. Okay, so yeah, Kate, good job. All right, so we got 0.5, 0.1, 0.15, 0.2. I need to change that thickness. I don't like the way any of this looks. I'm sorry. .05. Thank you. I'm sure someone's like, oh, what is she doing? That makes sense because if this is .25 and then I double it, I should get to .50. Hooray. This is okay. Olive Grace, would you let Sophia out, please? Thanks, sweetie. All right, and we want 40 to 80.
Can I please help?
Oh, what? Yeah. Hold on. Yeah. So it's wanted to know the region between 40 to 80. So 40. Ollie, hold on. I got a couple more questions. 40 meters is .2. Remember, it's micromoles. But your units are going to cancel out because it's percent. They already gave it to you there. And then at 80 meters. Oh, gal, not yet. Not yet, lovely.
Mom, can you help me get my magnet box thing?
You're going to need to tell me more about what's a magnet box thing.
It's where
That's .2.
all the magnets and you get checked for doing stuff.
2.0. Oh, yeah. Give me a second. I'm going to, right now, you maybe don't know because it's not a video, but I'm like recording my screen and my talking and you're talking. Okay. Okay, so how much did that change? We know that it increased with depth. We know that it increased, right? Because it went from, so even though like, sorry, final minus initial, it really doesn't matter. Like you just need one, we can tell that this is increasing because it's going in this direction and we know that the number 2 is greater than .2. So we know that number went up. So that is the difference when you subtract it. I'll fix that for you just for the sake of being a better person. All right, so where did you end at, but where did you start all over your starting point? Okay, and we can tell that it increased because it's going in that direction. Numbers increase going in that direction. So 2, Olive, can you eat on the couch? Thank you, sweetie. Take it to the table. Say, excuse me, Sophie. Thank you. Just move it. Just go. Walk. Move. She'll move. All right, what we're 1.8. Okay, all over the initial. So where did you start? Like, here's how far you came. You moved 1.8 micromoles. But where did you start at? .2. I don't like the way that looks mathematically. Okay, and a percent needs to be out of 100. So I would always tell you this in class too. If it's like you get a 5 out of 10, you divide that, you get a 0.5. That doesn't mean you earn 0.5%. You got a 50%. I'll get that for you. So if you need to then multiply by 100 to see it in an actual percent, then please do that. Otherwise, this won't be correct. Is this too hard to open? You're going to have to wait a moment. I can't do it with just one hand. All right, 1.8 divided by 0.2. 9. Did you get 9% increase? No, a 9% increase would be like what? 0.2, like not that much. Like almost near 0.3. All right, take one. Put this back in the fridge, okay?
Yeah.
Thanks, Ollie. 1.8 divided by 0.2, you're gonna get 9. It is not 9 though. You need to do 9 times 100, 900%. It's a big increase. So that's how much it changed from like the original, going from here
To here.
to here. How did you know I would say that? Yeah, so this whole thing is 900%.
Can I try and open it?
Sure can. Do you know how to do it? You gotta poke it in this.
Okay, Mom.
And put this in the garbage. No, 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 no. Not by the couch. Thank you, sweetie. Put this in the garbage. Thanks, sweetheart. Oh, man. Suggest why the region between 40 and 80 shows the greatest percent change in nitrate concentration. All right. I'm.
Can you help me open it?
Yes. Hey, Olive, can you just let me finish this, please? Please, 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 please.
Please,
No, the
please.
answer is yes, Mom. Thank you, sweetie.
Please, please.
Okay. And it's above an abyssal plain. Well, what's below an abyssal plain? What's up here? Look at your depth as well. You're going to have the most amount of well, you can kind of tell where the organisms are, but and it's the North Atlantic Ocean. Okay, so it's colder. So your photic zone, it's on average, sure, it's around like 150, 200, but in this situation, it's much colder. Doesn't tell you like a time of year, but still, it's the North Atlantic. Um, it's very low right here. And why would it be so low? Like, where is it going? And then all of a sudden, it picks back up again. Organisms are taking it in. And that's that suggest, like, apply your knowledge. The 40 and 80. Here's your 40, and here's your 80. Why is there so much right there? Like, did it just appear? No. Organisms are not taking it in. It's like, and who takes it in? Producers. It's not for animals. It's not for consumers. If they eat nitrates, they're gonna die. That's like feeding them fertilizer. And this like is a little difficult too because you would need to realize, okay, they said North Atlantic. So like this is like your equator. Here's good old America. There you go. And then, I always do such a good job with Africa. North Atlantic's like right here. I have friends in Europe, right next to Africa, apparently. Fabulous. This is embarrassing, but I don't care. So North Atlantic. So the sunlight is not going to be as strong. Low, not decreasing, but low light penetration. Okay, and I'm putting that there because it's the North Atlantic. Therefore, lower productivity. Productivity is the rate of organic material production. Which means there's fewer organisms. Or you could say less producers, or this is an abyssal plain. It's right above an abyssal plain. So they really wouldn't be able, the abyssal plains down here, way down there. So they wouldn't be able to like attach that substrate anyways. Like a producer, it's gonna have to be your phytoplankton. And then like where would it come from? I had to look this answer. I don't know. 3 marks. Trash. Excreted material. Hmm. Yeah, I mean but that just goes with like how do nutrients get put into the ocean or where do they go? Majority of the time they're either going to sink to the bottom, but we didn't see it sinking to the bottom. We saw it being depleted towards the surface. We saw it being depleted at the surface. And so what's taking that in? The only things that are at the surface, honestly, which are your organisms, but producers are the only things that can take in inorganic ions, nitrates, etc., phosphates, sulfates. The data shows in Figure 6.1 that were collected to investigate the effects of storms. So I'm thinking about like churning up the sediment, especially when we're talking about nutrients, on the concentration of nitrate ions in the surface waters. So storms, high wave action, lots of wind, moving sediment up. They were collected during a period of calm water. So the data shown in 6.1 were collected to investigate the effect of storms. Okay. They were collected during a period of calm water. Describe, so what and why, the differences you would expect to find in the data after a storm with very strong winds. Okay, so high winds will cause more water movement, or you could say it'll like create, or not even create, but increase ocean currents. If offshore winds could cause upwelling, deeper water, and this would cause an increase in nitrates in the surface water. So instead of it being low at the surface, here it was very low. You're going to see it kind of pick back up again. And not just that, but also like maybe toxins that settled, bacteria. Same reason why we're not supposed to go in the ocean when we're having a hurricane. Last one, suggest and explain. So what do you think, and then why? The effect of an increase in the surface concentration of nitrate ions. So up at the surface, what else is at the surface? Phytops. Now, if we have an increase in nitrates in the surface, you get water, baby. You see, it's right there on the by the sink, and then use the refrigerator for it in the bathroom. This is my last question, Ollie. Nitrate ions on the concentration or the amount of dissolved oxygen. Okay, so when I see this, I'm like, how does like a nutrient like nitrate affect oxygen? However, when I see surface, I'm like, duh, phytoplankton. Also, when I see nitrate or magnesium or sulfates or phosphates, I'm like, that has something to do with animals. Animals cannot do anything with that. It needs to get into the biotic phase so it can be put into an organic material, and then animals can come into play. But that is all producer magic. That is everything that a producer does. They are producing. So you're going to take what is not alive, the nitrate ions, synthesize it to what is alive. And my first thought was, and there's a couple different answers for this, but my first thought is you're going to have more producers because you got more nitrates. Nitrates are used for DNA, RNA, ATP, also for proteins, enzymes, amino acids. Amino acids make proteins. An enzyme is a protein that speeds up chemical reactions. So if we are having more producer populations, then because now they have more nitrates, then perhaps there's going to be more photosynthesis, more oxygen. That's my thought. But if you go from that step, like increase on your producer, which equals higher O2, well, the food chain follows. Now you're going to have an increase in consumers or feeders. And that's going to equal a decrease in O2 because they're going to do respiration. Yes, plants do respiration, but they also release oxygen. Consumers don't release oxygen. All they do is take it up. But my first thought was this one. So photosynthesis will be happening faster. So productivity. Your mark team actually has these flipped around, and that's fine. They said oxygen will increase due to increase in photosynthesis. Why? Because there's a higher productivity in the producers. Okay. Or we could say O2 will decrease due to, but I mean, in order for this next part I'm writing, the or, you could say, like, you still, in order to get this mark that I'm going to write, you would still have to, like, consider the first part of your producer population. But oxygen can decrease due to an increase in respiration. And then explain why. This is the why. This is the why. Or no change, right? Because concentration, nitrate ion concentration, that is a number. Numbers can increase, decrease, or stay the same. So you could say there's no change due to both photosynthesis, so releasing oxygen, and respiration happening, taking in oxygen. Both increasing. Woo! Oh my gosh, you guys. I am like, listen, as long as you're following these with me, you're practicing it. Some of these answers, you're like, wait, I wouldn't have wrote that. Guess what? I wouldn't have wrote some of them either. I've been doing this so long. So, but practice is helpful. And is at the end of the day, you've done all you can. If you've been putting your focus somewhere else for the past 3 weeks, 1 month, or you wouldn't even know this right now, maybe because you're not listening to me give you this little spiel and lecture. But do everything you can. And even if you're like, I wouldn't have got this right, you have basic skills required. You have basic knowledge. Sometimes these questions that are suggest how you have to apply knowledge to something, like the amount of inconsistencies and some like little errors here and there that I've seen in the recent year is mucho. And yeah, just give yourself some grace. You guys are gonna do good.